And welcome back to the series on Chebyshev polynomials, and we are going to talk this time about weak star convergence. Now, I debated whether I should even cover this in detail because it can get pretty heavy into the topology, but ultimately I decided, yeah, we need to talk about it a little. That said, I'm not going to try to justify or prove the major topological theorem that's going to be invoked in here. So the definition is actually pretty simple, I think. Weak star convergence says if we have a sequence mu n of finite positive measures with all these supports contained in a finite K, or sorry, a compact K. And as a rule, if you see a capital K, it probably means a compact set. So if I forget to say it, you should just assume that it is compact. Then we say mu sub n converges weak star to mu, provided the limit as n goes to infinity of the integral of f with respect to mu n equals the integral of f d, excuse me, d mu for every f that is continuous on K. Script C. So the statement involves continuous functions. Basically, the integrals work the way you would like them to. This limit here is able to move inward and change that d mu into some specific d mu. So note what we're saying here then. This is a sequence of numbers. We are integrating finite positive measures, so we get numbers, and this is also a number, probably a real number. So I guess it could be complex. Yeah, it depends on what f is, but we're talking about a sequence of numbers converging to another number, and we're saying if that sequence necessarily converges so that it matches up with this specific function on the same function on a separate measure, then that measure is the weak star limit of the other measures. And this gets a little into the idea of dual spaces, the idea of transformations, or in this case, measures that we're integrating on being identified with a number that comes out of them. And that's where I'm saying I don't want to get too heavy in, because dual space is one of those things that I've run into a few times and never really got a solid grip on. So I'm going to explain it as we need to. But the equivalence says that there's a uniform bound on all those measures. So all the measures of K for all the different n's are less than some constant, the same constant for all of them. Then they converge pointwise in the dual space. But I don't really want to get too much into that theoretical side. I want to focus on a few examples here, because one of the main ones we're using, one of probably the most useful ones, is the counting measure. So for some an, which is a finite set of n elements contained in C. Could be some other set, but we're specifically going to go with C. We say nu of an, or just nu sub n in some cases, is 1 over n times the sum from k equals 1 to n of delta z sub k, where delta z of anything is the unit point mass at z. So this is one of these cases where mathematicians come up with funny, complicated ways to say pretty simple ideas. In this case, we're just saying we count up how many elements there are in how many members of an there are in a set, and then divide by n. So if we pick out 12 points, then its measure would be 12 over n, if they're all from an. And then measure theory then to integrate would simply mean, if we want to integrate f with respect to d nu n, that is saying we are going to take the function k equals 1 to n, evaluate it at all those points, and then divide by n. So integrating with respect to counting measure just means we evaluate the function at a selection of points and then divide by the number of points after we add them up. Take the mean, arithmetic mean of the values at those points. So let's do an example. Let's say an is the set of the nth roots of unity. That is to say, on the unit circle and the complex plane, all the different evenly spaced points along there, each one of them when raised to whatever power gives 1. And we could say d theta is arc length. Then we're going to say that the measure nu of an will converge weak star to 1 over 2 pi d theta. So what this is saying then is that as we make an get larger, the points we are picking, they start to get more dense. And then we keep increasing n, so we keep getting more and more points along this circle. At some point, it would be the same or close enough that it would be the same as if we just integrated along here with respect to the arc length in the standard calculus 1 way, well, maybe calculus 3 way, and then divide by 2 pi. Why is that? Well, let's see what we would get. So let's partition 0 to 2 pi into p would be the exponentials of 0, 2 pi times 1 over n, up to 2 pi times n minus 1 over n. So that's just how we define the roots of unity. We travel intervals of 2 pi over n. I guess I should have I in this. In order to pick different points along there. So we can do a Riemann sum here. I know in measure theory, the Lebesgue integrals are more common, but since this is continuous, our rule was the weak star has to apply for continuous functions. And with continuous functions, Riemann's just as good. So the left-hand Riemann sum, we would say it is, well, we have n intervals here. So we'll define it as from k equals 0 to n minus 1, f of e to the 2 pi I k over n. So that's the value at each of those points times the width of each interval is 2 pi over n. And then if we were to take that limit, just by the definition of how Riemann sums work, they always converge to the Lebesgue integral, or to the Riemann integral, I should say, the integral. Converge to the regular integral, 0 to 2 pi of f of e to the it dt. So that is written as an arc that traverses the entire circle, f of e to the it, where t ranges from 0 to 2 pi. Okay, now what if instead we integrate that same function with respect to the counting measure? So we've got here is, this right here is the Lebesgue measure. It's just dt, t is the length. So let's say, what is the integral of f of e to the it d nu of an? Well, by definition, this is the normalized counting measure. So we sum f at all the points in an and then divide by the number of points there are. So that is the 1 over n. I have notes here and I want to make sure I don't make any mistakes. So if I take a little while to write stuff, that's why. Okay, 0 to n minus 1 of f of e to the I 2 pi k over n. Might have made some mistakes using I there. I think I might have made a small mistake there with the i's being in two different. Maybe it should have just been e to the t, and we get the idea, right? We're plugging in the different points. Like I said, maybe I should have defined the points as not being I, but as being just without the i's. I'm not gonna worry about it. It's a minor thing, and if it's too confusing, I'll redo it, but I don't think it is. So that, well, if you look at that, it looks almost exactly the same as this, except for that 2 pi there. So that is equal to 1 over 2 pi L. So therefore, the nu of an, the integrals converge to 1 over 2 pi times the limit, as into infinity, of L. But that limit of L is the integral, the Lebesgue integral. So it becomes just 1 over 2 pi, the integral 0 to 2 pi of f d theta. Okay, so there's the basic idea there. By picking these points, we can formulate them into a sum, which we already know will converge to the big integral, and then show that it converges to the same integral there, give or take a multiple. And the same thing will happen. There's nothing special about the roots of unity, really. What was special is that the points are dense. So another example that Saf gives, I'm following E.B. Saf's paper mainly, although I switching things around, but the exponential of lambda k pi I, where k is 1 to n. That looks like a j, and I'm not an engineer, so let me make that an I. And this would do the same thing, basically because the points are dense if lambda is irrational. So because they're dense, they will fill in the circle the same way and end up converging to the same thing. In the sum terms, you could say no matter how we partition it, we could find a point of this type in every interval. If lambda is rational, it doesn't work that way. And the reason is because eventually, if a rational multiple of the circle, it will eventually start repeating itself. At some point, we'll just have the same points repeating over and over again. And once we get to that, we're just going to end up averaging on that particular set of points, which is not the same as integrating over the continuum. Okay, so that's the idea of weak star convergence, which, like I said, I'm trying to stick with more examples so that it doesn't seem overwhelmingly weird. Let's give another definition. Let's say we have a function f that's mapping D, which is a subset of the complex plane, into negative infinity to infinity bracket. So note I'm allowing infinity to be a value of this function, but not negative infinity. F is lower semi-continuous provided, and then there are three separate characterizations of this. One, it could be that if you take the inverse of any set, half open set from alpha to infinity, closed on the right, open on the left, that is open relative to D for any alpha in R. So the topological definition of continuity is that the preimage of an open set is open. Here we're saying if these half open sets that go to infinity on the right, their preimage is also open. So that's the purely topological version. The second one would say for every z naught in D, f of z naught is less than or equal to the lim inf as z approaches z naught f of z. The lim inf, if you don't know, I like Walter Rudin's definition, which is the infimum of all the subsequential limits. So all the different subsequences that converge to z naught, if they don't have the same limit, the overall, it's not continuous there. But what we're saying here is that the actual value is lower or equal to any of the subsequences. And the third version says if in addition K is compact, then there exists a sequence of continuous functions on K that increase to F pointwise. So this lower semi-continuous F, we can come from below with actually continuous functions, but not necessarily from above. Now, these three definitions are all equivalent, but I'm not going to prove that because that would be a pain and it's not really necessary. I'm just going to do a little picture, proof by picture, if you will. So, and I want to show how all three of these definitions apply here. So here's an example. I'm going to draw a pretty basic example here. We'll do like this. So this point on the left would be, let's call it -1, -4. And the top will be -1/5, -1. This whole here is -1/5, +1. And then this top point would be 1/5. Okay, so the K in this case is -1 to 1. We want it to be a compact set, so the function is defined on that point. And this other one, I'll do the exact same thing, consider the numbers the same, but I will make the hole at the bottom instead of the top. And that's really the difference, is that when we have these breaks where it's not continuous, you fill in the lower hole. Let's see why this is. Let's do some examples here. Well, F inverse of 0 to infinity. Well, what are all the points that map something somewhere between 0 and infinity? That would be -1/5 to 1. Yes, and that, oh, the 1 should be included. I'm sorry. I had a little moment there. I was thinking that's not open, but it is open relative to this set. If I included the set 1/5 to 2 open on both sides and intersected it. So this, yeah. So intersecting a larger set with the universe, if the larger set is open, then it's open still. So this counts as open. 1 on the right, all its open neighborhoods will still be contained in K because there is nothing to the right of 1. So that threw me for a second because I saw that and thought it wasn't open, but it is open relative to K. Now, on the other hand, in this case, that 0 to infinity would give us -1/5 to 1. And that is not open because even with that whole relative thing, the point at -1/5, we can take an interval like that. And so 1/5, -1/5 is not a interior point, therefore the set's not open. Okay, so that's the first definition. Now I want to look at the second definition. I want to look at all three. So let me clear this off. So the second definition, well, I say, what are the subsequential limits here at the point where it breaks? Well, there's two options. We're coming from this direction, we get -4. we're coming from this direction, we get 1. So the lim nth is -4. And f of -1 is also -4. So the f is less than the lim nth. But over here on the right, the subsequential limits are still -4 and 1. I just erased that. I don't know why that erased. Well, but the actual value this time at -1/5 is 1, which is greater than the lim nth. So that violates the second definition there. So the right one is not lower semi-continuous. And the third definition, well, we try to find continuous functions that come at it from below. Well, if I want to do that, I could do something like this. I could just say really close, and then I could sort of cut through here so that it comes up close below. And that is okay because of the point being filled in at the bottom. It works. So to try to do it from here, I'd have to stay close right up to this point. And then there's no way I could jump up without missing this point here. The point there, if it's going to be below, has to be at least, the difference has to be at least this big. So there's no way to make it actually converge to that upper point there, because it's got to be below the lower branch. Okay, so that last one is the hardest to visualize. It's the most measure theoretic version. So when we are doing integrals with measures, it will be useful to do. I find 2 is probably the easiest for people who are not into topology to understand. But I want to emphasize that that was an example in the real numbers. We're more commonly going to be in the complex plane here. So I pick a point somewhere that's z0. There are many different paths. In the real numbers, there's really only 2 paths, come from below or come from above. Where in C, we can take any number of different paths. And each one of those paths will have its own subsequential limit. And so the point is, if you think of it in like sort of a topographic map, that all these different trails will lead to different points, and the f of z0 is going to be defined as either the lowest of them or something even lower. Okay, now another theorem, which again I won't bother proving because we talked about before, but one of the best things about compactness is they allow us to reach the extreme points. So on a compact set, an LSC function attains its minimum, but not necessarily its max. And again, I will just try to justify this through picture. If I had a function look something like this, I'm allowed to, this is okay because the lower part is filled in. Then let's say I go up and there's a hole at the top that it jumps down to here and then down here. This is lower semi-continuous because each point where it's not fully continuous, if you have choices of where to fill in the dot and you pick the lower of the two. So we can see there's a minimum here, but we can see this up here is the supremum. Make sure this is a little, let me erase here just to make it a little clearer. So that point is clearly the supremum. It's higher than any other point, but it never actually gets there because of the lower semi-continuity allows it to jump down. But it does achieve the minimum because wherever the point is where it approaches the infimum, it must approach it somewhere for it to be the infimum, and then the actual value will be that infimum. or perhaps even lower. Again, it could be there's a jump here down to an even lower point that's not the limit of any subsequence. No matter which way you approach, it's not going to get to that point. It's not going to approach that. But then that's the minimum as well. So that's not a problem. All right. So knowing this, we're going to need to have a few facts that we can apply. So let F be lower semi-continuous on K. K is compact, like I said. Mu n be a sequence of measures that converge weak star to mu. And the supports of these mu n are all contained in K. If you don't remember, support is in K just means that it's 0 outside of K. And since K is compact, I don't think we have to worry about closures, which sometimes is part of it. So I want to show a result which, again, SAF just states that this is obvious kind of thing. And so it took me a little time to spell it out here. The integral of F d mu, so integral with respect to limit, equals hold on, the okay, let me back up a second. Because F is lower semi-continuous, we know there exists some sequence F M that converges upward to F. That is to say, given any specific point, if we plug that point in K into the different F's in sequence, it'll be an increasing sequence that converges to whatever F's value at that point is. So that's using definition 3 of lower semi-continuous. Well, then this is equal to, we'll pull F back as to the lim inf. I could use limit, but I'm going to use lim inf here as m goes to infinity. If the limit exists, then the lim inf is the same thing because all the subsequences converge to that. And then I'm going to use what's known as Fatou's lemma, which is lim inf of m goes to infinity of the integral of fm d mu. So it just says, can you switch integrals? Well, the left side, the smaller side says slim. That's why it's the smaller one. That's how I remember it anyway. Now, we've now pulled back, and the point is the FMs are all continuous. Because they are continuous, we can now use the weak star criterion. We can say this is equal to the lim inf as m to infinity of the lim inf of n to infinity f of m d mu n. So that's what all we're saying there is we're pulling back to the sequence of measures. I could probably use regular limit in these, but I'm using lim inf because Fatou's lemma, I felt like using it. So now let's switch the order of the lim inf. That's allowed. There should be an integral sign in here somewhere right there. So this is the same as lim inf n to infinity lim inf m to infinity integral of f m d mu n. Okay, so now we're taking the integrals using the proposition 3 again. The f's are going to converge to f, or the, sorry, let me say that properly. The fm's are all less than f itself, so we can replace that using just linearity of measures with lim nth n to infinity of integral of f d mu. So that's a short proof there, which used a few things. We said we pulled back from f to the lim of the fm's. We use Fatou's lemma to push the integral sign inside. We then pulled out the measures, changed from d mu to d mu n, which we use a weak star, and then we what was the next step? We switched the limits in order, and then we took that limit of the inside here to change the mu n back to mu. So the conclusion then, which will be needed a few times, is that the integral along k of f d mu is less than or equal to the lim nth as we take n to infinity of the integral of f d mu n. And so what this kind of means is that the measures sort of inherit the lower semi-continuous property, that the lower semi-continuous property says that f is less than or equal to the lim nth as points approach z naught of f of z. And we get kind of the same thing here. The integral with respect to one measure is less than or equal to the lim nth of the integral with respect to all the different measures approaching it. So lower semi-continuous somehow transfers that property to the measures themselves. Okay. Another way of saying it then is that you've got a whole sequence of measures. Even if they don't converge, there's the integral with respect to their limit is a lower bound for the integral with respect to any of the other measures. Or not with respect to their limit. I shouldn't have said limit because we don't know the limit exists, but, or, no, we do. Sorry, I'm saying this badly. The mu n converge weak star to mu. The various integrals f d mu n, if we pass along any well, we get numbers. Again, these are numbers. This is a number here, and these are all numbers. Yeah. F not, oh yeah, but it's because f is not continuous. So if f were continuous, these two sides, the lim nth would just be a limit. But since it's not continuous, it has to use lim nth because they might not converge with respect to the continuous function. Okay, so that was a roundabout way of me working that out in my head here. But basically then what we're saying is that if it were continuous, this would be an equal sign and this would be a regular limit. But since it's not continuous, so lower semi-continuous, we have to make those adjustments to give it a little more flexibility. Okay. Now we want to cover a few more things here. And we're still trying to gear up to that, finish that proof from last time about capacity and the transfinite diameter, the Fekete sets. So we're going to talk about the principle of descent. Make sure I'm still recording. I get a little paranoid about that. I want to make sure that I don't accidentally, especially when I had to pause earlier. All right, sorry about that. Principle of descent. And so this says, given mu n converges weak star to mu, where all this is happening in the set M of E. Let's say this time E is compact and ME are Borel probability measures. Borel meaning they contain all the open sets, probability meaning the measure of the entire set is 1. So all the different measures we have in mu n, they will all identify the total set E as having a size of 1. So U to the mu of Z is less than or equal to the lim nth of U to the mu n of Z. As n to infinity. So mu is the potential. So we're saying we've got a sequence of measures that are converging weak star, that the potential of the limit measure at any point is less than or equal to the lim nth, the smallest subsequential limit along mu n. And I mu, the total energy of the measure, is less than or equal to the lim nth n to infinity of I of mu n. So what we're saying here again with lim nths is that the mu n's are a sequence, and that the sequence converges weak star there means that continuous sets, they would converge, these things would be equal. And since potential and energy do have a big discontinuity in them, we can't say that it's equal, but we can say that the final result is less than or equal to any of the subsequential limits. So if we took a convenient subsequence of the mu n's and found its limit, we would know that it has to be, the actual final value has to be less than that. In physics terms, this is kind of an entropy statement. It's saying that as time passes, we watch the system evolve, the potential at a fixed point and the total energy on E both decrease to their equilibrium. That's what I would paraphrase that as. I'm not sure if that paraphrase is correct, because again, we're talking about lim nths and not actual limits. Sorry. After I said that, I realized that was not really the best way to say it. That was more like a limit, and we don't know if the limit really exists. But we're saying, what we're really saying is that the potential and the total energy are are below the equilibrium finitely many times. That's another way of saying it. Another way to say it might be there is some subsequence that does converge to that. There's a few different ways, and this is why I was a little reluctant to get into this subject, because I was worried that the peer analysis and topology would be a little iffy. If you're not intimately familiar with how lim-infs work, you can get a little mixed up in what they mean. But we're going to try to prove that the weak star limit of both of these is less than or equal to the lim-inf of the sequence that converges to them. So let's do a little proof, which will mostly be just combining things we've already talked about. So u to the mu of z is, by definition, it's the integral across k of the log of 1 over z minus t d mu of t. Now, what I want to say is that the function, the integrand here, if we put it in t, f of t is log 1 over absolute value of z minus t, is itself a lower semi-continuous function. How do I know that? Well, look at z minus t. Z is now a fixed point in the complex plane. So this f should be a constant along all points that are fixed distance from z, because absolute value of z minus t is just the distance between those two. Well, that means concentric circle. On a concentric circle, or a circle about center at z, this function f will be constant. So therefore, if I call this point here alpha, and we can see that as t goes to z, it will blow up to infinity, which is allowed in this case. The f inverse of alpha to infinity is an open circle. On the circle, it would equal alpha. So set of all points where it's greater than alpha is everything inside the circle. So the pullback of one of these sets is open. Therefore, the function is lower semi-continuous. So therefore, since it is lower semi-continuous, we can use the fact that we established, which is this k here, this integral with respect to mu will be less than or equal to the lim-inf as n goes to infinity of the integral of k log of 1 over z minus t d mu n of t. Okay, well, that is just reworded version of the potential. Just a second. U to the mu of z is less or equal to the lim-inf as n to infinity of u to the mu n of z. That's just for the definition. That's just the definition of what that means. So That's the principle that we were trying to prove. As for the second one with the I, well, it's sort of the same argument, but we have mu n converges weak star to mu. We can have a product measure, mu n cross mu n converges weak star to mu cross mu. I think this is an application of the Fubini-Tonelli theorem, which allows you to switch the order of the integrals. Regardless, that's what we're saying. The two different measures each individually converge to mu, so together they also converge to, well, they converge to mu cross mu. All right, so next step. Lemma 1.7 in SAF's paper is that we can achieve the Robin constant. So remember, the Robin constant was the minimum energy of the system. We're saying there exists some mu sub e in the space of all those measures, those Borel measures of probability measures, measure one, unit measure, however you want to call it, such that the energy of mu e is exactly equal to the Robin constant. And this says, this is where I'm really not getting into the topology, because he says it uses Helly's selection theorem or Banach Alaoglu. I have no idea, but all it's saying is that this measure space is compact, which to me just makes sense because they're all measure one. One is a singleton, it's a closed compact set. It feels right to me that the set of measures that do that also are compact, but I'm just going to take that on faith there. So RE, the Robin constant, is a limit point of M of E. It is the infimum. There must be some subsequence that converges to it based on compactness. So we can find a subsequence mu n that are all in the measure of E, and the limit as n to infinity of I of mu n equals the Robin constant. Now, I emphasize this is not saying that the mu n's themselves are converging weak star, but we can find a convergent subsequence because of compactness. So there's some subsequence mu n k that converges to something. So just because the mu n's, their energies converge to the Robin constant does not mean that they themselves converge in the weak star sense, but they do have a convergent subsequence by compactness. And then the principle of descent says the I of nu is less than or equal to the lim nth of the I of mu n to infinity, which by definition of what is a lim-nth? Well, it's lower than all of the subsequences, so we could take the subsequence here, and that is the Robin constant. So we have now found a way of making say that this measure mu, whatever it is, its energy is less than or equal to the Robin constant. And just the definition of the Robin constant was that it's less than or equal to the energy of any measure. So therefore they're equal. I of nu is the Robin constant. So again, that was some really abstract topology there that if you're more of a physicist, you don't necessarily need to know. We're just saying there is, if we know that there's a lower bound on the energies, we can find a perfect measure that will actually reach that lower bound. So now we're finally able to finish the proof from last time. Well, let's have a quick little refresher of some notation. Fn is the endpoint Fekete set. That minimizes energy. Energy being En of E is the minimum Z1 dot 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 Zn in E of the sum from 1 less than or equal to I less than j less than or equal to n of the log of 1 over the differences. Or equivalently, so if we plugged in the Fekete set, it would actually reach that En, that minimal energy. Equivalently maximizes the geometric mean, which we denote delta N of E is the max for all points, which again will be achieved by the Fekete set of the product where we have this set up so there's no, it's a handshaking problem, there's no double counting. You'll notice also that we are avoiding any case where we have I equals j, which will be quite important in a moment. So the relationship here, let's zoom out a bit. I need a little more space. I want to put all these definitions on the same page. En of E is n times n minus 1 over 2 log of 1 over delta n of E, and tau of E is the limit as n goes to infinity of delta NE. And also we talked about the weak star measure just earlier. Nu of Fn or nu n is 1 over n sum of z delta zk. Just add them up and divide by n. All right, if you're trying to follow along at home, you might take a screenshot right now because I'm going to be calling back to these things without restating them. All right, so we're almost done. Okay, so we were trying to prove the equivalence of tau E and capacity of E. So the set here, nu Fn, since we're in compact space, we can find a limit point, weak star. Mu star is, or mu hat is a weak star limit point. That is to say, the new ends, maybe they don't converge in the proper sense, but they have a subsequence that does converge. So that's because the measure is, the set of measures on E is compact. So we will extract some new NK that weak star converges to mu hat. Now define log sub m of x is the minimum of log x and m. I was reluctant to use this notation just because it looks a little like you're saying log base m, but that's not something we really do in this sort of math. The log is assumed to be log base e in general. So this is just the way to do it. It's saying that at a certain point, when the log gets too big, we just flatten it out to m. So like go up, and then at some point you just go level. Kind of reminds me of a ReLU, something we were talking about with a neural networks class, which just sort of zeroes out everything after a certain point. Here it just flattens it. Same idea. It's not really, it's just something, a connection I made in my head. All right. So what we are going to say, why do we do this? Well, we can now say the limit as m goes to infinity of log mx equals log x and is monotone in m. It's increasing monotonically. So it's a sequence that comes from below to reach log of x. Now, the monotone convergence theorem is now going to come up. And that just says we're dealing with measure spaces. If we have a sequence of functions that increases to another function monotonically, then we can switch around the integrals and take the limit of the measures like that. So as we know, new nk cross new nk will converge weak star to mu hat cross mu hat. So I of mu hat, this is what we want to look at, is defined as the double integral of log of 1 over z minus t d mu hat of z d mu hat of t. Okay, well, we can pull the m out as a limit. This is the limit as m to infinity of double integral of log of 1 over z minus t with that base m there of d mu hat z d mu hat of t. And let me emphasize what really happened here is that this original function we have is that limit as m goes to infinity of log base m there. That's the same thing. Because they're increasing monotonically, we are allowed to pull the limit out. That's what the monotone convergence theorem says. Okay, because log base m of x will converge to log x just because eventually any given point will get to the point where m is so big that the log is the smaller option. Point-wise convergence. Always be some that are at infinity or larger than m. But anyway, where were we? Okay, so now that we have that, these functions are continuous, so we can pull out the weak star limit, the log m here is continuous, and it doesn't have an infinity point. I don't think we don't want that. And so the real reason we're doing this is because if z and t were equal, this thing would be infinity. But by replacing numbers that are too big with m, we can prevent this thing from blowing up to infinity. And it allows us to use some of these theorems that don't work at infinity quite so well. So that makes this thing continuous. There's no going to infinity. So we can now replace the measures with the sequence that they converge to. That's log base m of 1 over z minus t d nu nk z d nu nk of t. Excuse me. Now, let's evaluate this double integral. What is it we're really saying to do? Well, remember, these are counting measures. And this part in particular, SAF just really skips over and expects you to, I don't know, just understand it. So I'm going to expand on it quite a bit here. Let's work these from the inside out. We get the limit as m goes to infinity, limit nk goes to infinity of the integral of, and this becomes a sum. Remember what counting measure says. It says that we evaluate the function at each of the points and divide by how many points there were. So it becomes 1 over nk sum across all the zi that are in f of nk, the Fekete set of nk points, log sub m of 1 over zi minus t with absolute value d nu nk of t. If I ever forgot to put the absolute value in the log part, it should be there. So that's my mistake if I left that off. All right, so then this, we get a double integral becomes a double sum. Limit m to infinity, limit nk to infinity. And so this becomes 1 over nk sum of from tj Rn f of nk of 1 over nk sum of zi n f of nk log 1 over zi minus tj. So see what happened here. We just first summed along all the z's right here, and then we summed along the t's after that. Or maybe it's the other way around. Doesn't really matter. We're going in both orders. This log should still have an m on it. Apologize for that one. But that's going to become very important here. That's why I had to go back and point that out just now. Because here's the thing. If this were just log, we'd have n different cases here. We count through all the zi's and then all the tj's. There'd be n times where they'd be exactly the same. We'd be taking log of infinity, so that would blow up. But at those n places, we can just replace it with m, because we've said we take the smaller thing, whether it's the log or it's this m, and m is just a constant. I'll be honest, it could have probably done to explain what m is, but it's just some number, probably some really large integer. Anyway, I hope that wasn't too confusing. But our point here is that And there might be other cases besides those n. Those n points are definitely going to cause infinity, and so m would be the smaller of the options. Now there might be other pairs where it would also be smaller to take m, but we'll just stick with log for those. And so that means this is less than or equal to limit m to infinity, limit nk to infinity, 1 over nk squared. I'm pulling out the two nks. And so we will get the sum of all the places where I is not j, log of 1 over zi minus tj, plus m nk. So again, what we're saying here is we might have a whole bunch of points where the m is smaller than what the log is, but we are only going to round down the ones that actually gave us infinity. It may be that we could round down more of them to m to make it even smaller. We're not doing that. We're just going to say this case here is the largest, or is larger than it would be if we actually worked out the sum exactly. Yeah. So yeah, I feel like I could overstate this one, but yeah, we're replacing all the points where they're equal with m, and we're taking as the fact that maybe some of the other ones are bigger. But now we're just replacing with regular logs, so the ones that other m's are just going to take the larger. All right, so like I said, it took a while thinking through that one, so I just want to try to explain why it is the way it is. 1 over nk squared. This here becomes 2 en of e. And this is similar to the, we talked about this in the previous case. Since I is not equal to j, we have double counting. Because the definition of en said I is less than j, but we're also including a case where I is greater than j. So every ij pair gets counted twice. So that's why we have a 2 there. Plus mn sub k. Now let's simplify this a little. This becomes limit m to infinity, limit nk to infinity, 1 over nk squared. And just go back to how e sub n of e was defined. And we end up with nk minus 1 log of 1 over delta nk of e plus m nk. Yeah, there was that whole n minus 1 factor involved, and there was also a 2 that cancels out the 2 that we have above. Well, this, let's see, reduce that a bit, just do some arithmetic, some algebra here. That'll become 1 minus 1 over nk log of 1 over delta nk of e plus m over nk. Unfortunately, they were doing the nk limit first. This is a case where switching the limits would probably change the result, but we get limit m to infinity. This goes to 1. This goes to log of 1 over tau e, because that's how we remember tau of e is just the limit of those deltas. So if we're taking the subscript to infinity, we get tau e. So this is log of 1 over tau of e. And this piece, the nk, goes to infinity. It zeroes it out. So that's just log of 1 over tau of e. And then if we go back a ways to the end of last video, what we showed was that log of 1 over tau e is less than the Robin constant, less than or equal to. And that was just something we proved last time. You can go back and review if you need to. It was towards the end of the last video. Okay. Now, again, by definition, the Robin constant is the minimum of the energies. So the Robin constant is itself less than or equal to I of mu hat. And I of mu hat, this whole long chain of inequalities, if we go back to remember, let me just scroll instead. Excuse me, wrong button. Go back up here to the very beginning. The first thing we wrote was I of mu hat. I of mu hat equals less than or equal. Keep going, da, da, da. It was a lot of writing, wasn't it? But I of mu hat was less than or equal to this thing that we ended with, which was R of E. So R of E is less than I of mu hat. I of mu hat is the beginning of this chain, so it's less than or equal to log of 1 over tau E. I think I said less than instead of less than or equal, which is itself less than or equal to R of E. Oh, look at that. Log of 1 over tau is between a number and itself. So therefore, they must all be equal. So there's our conclusion from all this. The Robin constant is equal to log of 1 over tau. So let me clear the canvas here and put the bow on this. The Robin constant is equal to log of 1 over tau of E, which, that's the negative log of tau E. So negative the Robin constant is log of tau of E. Raise both sides to E. The left side is how capacity was defined. It's E to the negative Robin constant. The right side is tau E. There we go. Whew. So that was some work. Now let me just cap off with a couple little observations of why this is so useful and what its implications are. Well, for starters, when the capacity is positive, there is a unique equilibrium measure. The capacity is 0, then you can measure it however you want, you'll still get 0. But when the capacity is positive, the equilibrium is unique. So that mu hat is the equilibrium measure because it was the limit there. Well, the mu hat was the limit of the counting measures. So therefore, those new n's converge to the equilibrium measure. I'll just call it regular mu now. Or mu e, I think that was how we were saying it earlier, the equilibrium measure. So there we go. For positive capacity sets, there's only one measure that is the equilibrium measure, and so it must be the limit of the counting measure on the Fekete sets. So that is useful because it gives us a way of finding that equilibrium measure or of estimating it to whatever degree of precision we like by taking larger and larger Fekete sets. It also tells us that we saw earlier, last time we talked about the maximum modulus principle, says the Fekete sets have to be on the boundary. So let's say I have some oddly shaped compact set. Let's put a hole in there. Well, the Fekete sets will be points along this outer boundary. We'll fill in as we go. I am just guessing where they would be, just trying to space them out. But as we keep adding, it will gradually fill in the entire boundary. So what we have is the capacity of the set E is the same as the capacity of its boundary. This del infinity E is notation Saf use. It means the boundary that is adjacent to infinity. Infinity is, out here somewhere. This is the boundary that's closest. Boundary that. So in addition, then the measure that the equilibrium measure for all of E is the same as the equilibrium measure on just the boundary. So we're always just going to be using the boundary measure. And if del infinity of E, the outer boundary, is a continuum, then the limit will fill in the whole set of the Fekete sets is del infinity of E, except maybe for a polar set. So it's possible we could have some strange piece of the boundary that does not have any of the energy on it, any of the measure, but that will be a polar set. It will be small, capacity 0. So we can conclude that with saying that the support of UE is almost all of it, or rather I should say the boundary of E, take the whole outer boundary of E and take away the support, the part of it where the equilibrium measure is supported, that has capacity 0. So again, we have that case where there's a very small exception. The measures everything on the boundary except for a very small capacity 0 or polar set. Okay, that was a lot of work, but it got us to our big conclusion. Our big conclusion tells us something about how the Fekete sets and the capacity are related. And that all seems kind of physicsy. And I went a little out of order from how Saf did it, mainly because I wanted to justify it with a little bit of this physics explanation. But now, next time we have the groundwork laid, we will go back around and tie this all into the Chebyshev polynomials, which is where we've been aiming at the whole time. I will see you then. Bye.